Hello and welcome to another GCSE revision video, and in this video we're going to be looking at tree diagrams. A tree diagram is a way of graphically representing all the possible choices or outcomes of mutually exclusive and collectively exhaustive events. A binary tree diagram, where there's only two possible outcomes, might look something like this. But where there are more than two outcomes, the diagrams can quickly get complicated. So make sure you plan ahead when drawing a tree diagram and make sure you've got the right amount of paper and space. Okay, so what's a tree diagram good for? Well, the purpose of a tree diagram is to list every single possible outcome, that is to say, our sample space, to make it easy to work out combined events. For example, what is the probability of tossing first a heads, then a tails? Well, saying what's the probability of tossing first a heads, then a tails is the same as saying what's the probability that toss 1 will equal heads and toss 2 will equal tails. So when we travel along a branch from one event to the next event, we multiply the probabilities according to the AND rule. Okay, so what is the probability of tossing either a head or a tail on the first throw? Well, we already know from the previous video it's going to be 1. 0.5 plus 0.5 is 1. The events are mutually exclusive and they're collectively exhaustive, so yeah, of course they're going to be 1. When we're considering different branches of the same event, we add the probabilities. If the tree diagram is complete, the sum of all the probabilities attached to a single event would be 1. So we would add the probabilities according to the OR rule. If we navigate all the way through to the very end of each branch, we can say that the final probabilities are the leaves of the tree. And if we sum all the probabilities of all of the leaves of the tree, assuming the tree is complete and that the probabilities all represent a collectively exhaustive and mutually exclusive events, then we can say that the sum of all the probabilities of all the leaves are 1. Okay, let's try another problem. What is the probability of tossing at least one head after 2 coin tosses? Well, our probability of tossing one head is, or the first coin, will be 0.5. And then the second coin, it can either be heads or tails, and there's a 0.5 chance of it being either. So the probability of it being heads and then heads is 0.5 times 0.5, which is 0.25. And the probability of it being first heads and then tails is 0.5 times 0.5, which is 0.25. So the probability of at least one heads, if the first coin is heads, is 0.25 plus 0.25, which is 0.5. And you'll note that the sum of the probabilities of the leaves at the end of the branches is the same as the probability of the previous branch. So we don't actually have to waste our time adding up or even considering what's going to happen. If the first toss is a heads, we don't really have to care about what the second toss is going to be because the first toss has already met our criteria. Now, of course, the first toss might come up tails, and then the second toss might be heads, in which case we have to consider the second toss. So the probability of at least one head is equal to the probability that toss 1 is equal to a head, plus the probability that toss 1 is equal to tails and toss 2 is equal to heads, which is equal to 0.5 plus 0.5 times 0.5, which is equal to 0.5 plus 0.25, or 0.75. Another or even easier way we could have looked at it is to observe that the sum of all the possible outcomes is 1. So the probability of getting at least one head is the same as 1 minus the probability of getting 2 tails. So the probability of at least one head is equal to 1 minus 0.5 times 0.5, which is equal to 1 minus 0.25, or 0.75. Okay, well, so much for the theory. Let's have a go at putting this into practice. This is a question lifted from an actual GCSE sample paper. It says, here is the probability tree diagram. Work out the probability of winning both games. Okay, so the probability of winning game A is 0.2, and the probability of winning game B is 0.3. So we're going across the tree, so we remember we need to multiply. So the probability of winning game A and winning game B is 0.2 times 0.3 is equal to 0.06. And that's the end of that actual question for the exam. Let's look at another just to really ram home how these probability trees work. A and B are two sets of traffic lights on a road. The probability that the probability that a car is stopped by lights A is 0.4. If a car is stopped by lights A, then the probability that the car is not stopped by lights B is 0.7. If a car is not stopped by lights A, then the probability that the car is not stopped by lights B is 0.2. Complete the probability tree diagram for this information. Okay, that's a lot of information, and it's easy now to see why we need probability trees. It helps to lay out confusing information so we can get a clear visualization of what we're being told. So we've got lights A, and the probability that the car is stopped by lights A, we're told in the question, is 0.4. Now we know that going down, the probabilities must add up to 1. So if this is 0.4, then this must be 0.6. So the probability that the car is not stopped by lights A is 0.6. Okay, we're told if a car is stopped by lights A, then the probability the car is not stopped by lights B is 0.7. So this, if it's stopped by lights A and not stopped by lights B, that's 0.7. Okay, so again, this will need to add up to 1, so this has to be 0.3. And now we're told if a car is not stopped by lights A, then the probability that the car is not stopped by lights B is 0.2. Let me just read that again to get it clear in my mind. If a car is not stopped by lights A, so that's coming down here, then the probability that the car is not stopped by lights B is 0.2, so that's here is 0.2. So if the probability that it's not stopped is 0.2, then the probability that it's stopped has to be 0.8, because the probability that it's stopped or not stopped has to be 1. And that's completed our probability tree diagram. Now we're told Mark drove along this road. He was stopped by just one of the sets of traffic lights. Is it more likely that he was stopped by lights A or by lights B? You must show your working. Okay, I think this might be slightly badly worded, because the phrase "he was stopped by just one of the sets of traffic lights" sounds very much like a statement of fact, which would lead me to think that, okay, there's a 0.4 chance that he was stopped by lights A. Given that he was stopped by just one of the traffic lights, then there must be 0.6 chance that he was stopped by lights B. But that's not what the examiners want. For one thing, it's too easy. For another thing, I did actually take a sneaky peek at the one of my previous videos, actually, just to make sure that I was getting it right. And in that video, I'd looked at the marking scheme, and I know that that's not what the examiners meant by what they're saying. So, but given that this is badly worded, what they're actually wanting us to do is to calculate the probability that he was stopped by one of the satellite lights and figure out which probability is the higher. So we can start off with looking at the leaves of this tree. So if he was stopped by lights A and not stopped by lights B, then that's 0.4 times 0.7, which is equal to 0.28, which represents the probability that he was only stopped by lights A. So 0.4 would be the probability that he was stopped by lights A or by lights B or both. Now, the other option that he could have been stopped by just one set of lights is that he was not stopped by lights A, but he was stopped by lights B. So that's coming down here and then going up here. So that's 0.6 times 0.8. Which is equal to, well, 6 times 8 is 48, so that's 0.48. So the probability that he was stopped only by lights B is 0.48, and the probability that he was stopped only by lights A is 0.28. So the answer that they're looking for is B, with the correct calculations that we've shown here. Okay, I hope that was helpful, and I look forward to seeing you in another video. Good luck with your revision and good luck with your exams.